$1 million in prize money is on the line in the first ever head-to-head autonomous racing event to be held at the Indianapolis Motor Speedway in October. UVA Engineering's Cavalier Autonomous Racing Team will compete with other top universities for bragging rights as the best autonomous racing team in the world. Buckle up as I, your host, Chris Tyree, and UVA Engineering professor Madhur Behl take you in the shop, under the hood, and around the track in this new world, pushing autonomous vehicles to their limits.
Hi there, and welcome to the Lucas Oil Raceway Event Center, which is our makeshift garage space and workshop space where we work on our autonomous race cars while we are not on the track. The reason why we are here at this magnificent location is because of its close proximity to the Lucas Oil Raceway racetrack oval, the half-mile oval, where we actually go and practice and test our algorithms in preparation for the Indy Autonomous Challenge. Today I have something very exciting to talk about besides the team and our history of this challenge. I want to actually introduce the main star of the Indy Autonomous Challenge, which is this amazing piece of technology right here. In my opinion, this is possibly one of the most remarkable robots ever built. And we are fortunate to be working such close proximity and getting into, getting this amazing race car to get up to speed at Lucas Oil Raceway and eventually at the Indianapolis Motorsport Speedway. So let me maybe walk around, show you a little bit about how this car is put together in terms of the chassis and the hardware design. And then I will reveal some of the autonomy aspects of this car as well to give you a really good idea of what it takes to take a race car and convert it into a high-speed autonomous robot. So let's jump right into it. So this car is actually a Dallara IL15 chassis. Dilara is one of the most famous car manufacturers, race car manufacturers in the Indy Light series. I believe it is the sole supplier of all Indy Light chassis vehicles, and therefore this is as true as it gets, unmodified Dallara IL15 chassis that we obtained. And all teams get the same chassis, which is then converted into autonomous race car, as I will show in just a bit. So as you can tell, this car is made up of pure carbon fiber. So, this is what race cars are made out of. Carbon fiber is very lightweight, and it can sustain significant stress and significant pressures at racing speeds as well. This is powered by a Honda engine underneath the hood, underneath this part right here. It's, I believe, a 386 horsepower Honda engine, which gives it enough juice to go up to 180 miles per hour. So slightly faster than your regular sedan and SUVs. So we get the chassis from Dallara, and with help from our racing team partner, Juncos Racing, we put together and assembled the car in their workshop. So Juncos Racing has been helping all the teams with all trackside activities. They are great help to the entire competition. This competition wouldn't exist without their input as well. And so they are responsible for maintaining the car, for fueling the car, for adjusting the suspension, the aerodynamic aspects of the car as well. So when we go on the track and we want to try different speeds, the team from Juncos is ready on site to help us in whatever manner we want. They have even taught us, computer scientists, about the engine, how to crank the engine, right? So this is something that we typically don't do inside the lab when we are at our desktop working on code and simulation. So this is really, really exciting stuff for us to go out on the track, work in the workshop on the real hardware and real software, getting this car to work. So very briefly, let me touch upon a history of how this car came into existence. About 2 years ago, when the idea of the Indy Autonomous Challenge was floated around, the organizers, they partnered with the Automotive Research Center from Clemson University. And it's actually over the past year and a half that the team of students and faculty from Clemson University, they prototyped the autonomy aspects of this car. So they essentially designed on how you take a race car and convert it into an autonomous machine. So let me show you a little bit about the autonomy aspects and talk you through how is it that we can take a human-driven race car, and you can see there's no room for the driver to sit on this car anywhere, and how can we take this chassis and take this car and convert it into a fully autonomous high-speed robot. So come, check this out. So I will reveal the main cockpit. Let me put this aside. So inside what you might see is a mess of wires and harnesses and different ports, but to me, this is just beautiful sight, right? So let me walk you through what we are seeing here. Up top, you see three prominent silver boxes. These are very high precision LiDAR sensors from a company called Luminar. So these three sensors can report millions of, they send out millions of laser signals which report precise distances to everything around the car. And this point cloud of information that we get is very useful for us in detecting what's around the track and also detecting where we are on the track, and obviously helping in things like collision avoidance. We rely on this LiDAR sensor as well. Also, if you come in a little bit closer, you see all these cameras. We have 4 cameras in the front, and we have 2 cameras at the back. So overall, we have 6 cameras, which give us a good 360-degree field of view around what is happening around the car as well. This car also contains radar sensors. So you see on the side, we have 2 radars on this either side from a company called Aptiv, and then all these cars also have a front radar as well. So you can look at the velocity and track different objects in front of the car as well as laterally when you're overtaking on the side of the car as well. So if you come in a bit closer, you have all these sensors and they produce a lot of data. And you have a high bandwidth switch, which is pulling in high bandwidth gigabit connections to consume all this data. And right underneath this piece switch is the main computer, which is provided by a supplier called AD-Link. This is a powerful computer. It runs Linux on board, and this is one which is responsible for us to run all our software resides on that main computer as well. So this is how we do the autonomy integration of the car itself. But there's one more missing piece, right? How do we actually control the car? There is no steering wheel, as you can see in this vehicle. There are no throttle pedals, there's no steering wheel. So how are we controlling this car, you might wonder. And for that, what happens is, as we obtain the chassis of the car, underneath this piece, this front nose section right here, is a drive-by-wire system. Many modern automobiles already have drive-by-wire capabilities, but not a race car. A race car is meant to be driven by a human driver. It has 2 pedals, and the steering wheel has gears and clutch engagement buttons and many other control panels as well. So all of that actuation, all of that control has been migrated into a drive-by-wire system provided by a company called Schaeffler, which is also one of the sponsors of the Indy Challenge. And then this drive-by-wire system is controlled by an ECU, or electronic control unit, through which we can send software-defined signals and control the throttle, the brake, and the steering commands. So you don't see a physical steering wheel because it has been replaced purely by this ECU and the drive-by-wire system, which we totally control over software. And that's about it in terms of integration of the autonomy aspects of the race car along with the chassis. There's one more piece which will bring everything together. Because this is a race car and because we have to program it, we have to continuously analyze data back and forth from the car. When the car is on track and when the car is in the pit lane, we have to be able to remotely connect to the car in order to diagnose or even sometimes send safety commands. The race control has to be able to send some signals for the flat conditions on the track. So that brings me to this top part, the head of the car, if you will. This antenna is powered by Cisco, which is the main sponsor for the entire Indy Autonomous Challenge. And this antenna can connect to both the base station, which is every team's, you can think of the laptop that they use to remotely start the car and stop the car. And it also connects to the infrastructure on the racetrack. So we have a bunch of different radios on the entire racetrack. So no matter where the car is at the oval, we will continuously have some ear or telemetry signals coming from the car, knowing that it's working fine. If there's a cause for an alarm, if things seem erratic, then the race control can send a remote emergency stop button. Speaking of emergency stops, we hope that it never comes to it, but this car has emergency stop buttons on either side as well. So if it goes haywire and there's a risk of a fireball, then the safety team at the track itself can drive up, hit the button, and it'll kill the engine instantaneously. So that's a big safety precaution. We pay a lot of attention to safety, even though this is full-scale racing, and many people would think racing and safety are very contradictory objectives. That's not the case for this competition. Safety is a high priority, and we don't want these cars to crash unnecessarily. They're pretty expensive as well. You might be thinking, what does it cost to put this car together? And I don't have an exact number for you, but it's north of $1 million, roughly speaking. So while it's exciting to work on $1 million robot, you also have to be very careful to not cause it to crash, to be very careful about how you program, put all the safety checks in place so that all the pieces, the software, the hardware, they seamlessly come together with the mechanical aspects of the car, making it truly an interdisciplinary robot and experience for the students that cannot be paralleled and matched inside the lab whatsoever. And so that's about it. This is the AV21 autonomous vehicle, which is the standard vehicle to be used by all the racing teams in this competition. And come October, you will see this vehicle race, hopefully into triple-digit miles per hour speeds, screaming across the start-finish straight as they would in a real human-driven car. And that would be a sight not to miss.